All right, back from break. Just when we thought we had finished the midterm, look, there's another midterm. So again, this is a midterm that was given, I'm going to say several years ago, actually. So let's take a look at this. Now, again, what I'm guessing is that there's going to be a couple problems from those first three chapters, looking at electric force, electric field, electric potential energy, and electric potential. We'll see if those four show up. And then a couple of problems that involve circuits. And this time it looks like we've got a capacitor problem and a resistor problem, but we don't have anything with capacitors and resistors together. All right, so something to, pay attention to as we go through the problems. But let's go ahead and get started and see what problems we have here. So in this one, we have a set of parallel plates being used to accelerate charged particles. So if I'm going to use some parallel plates to accelerate a particle, let's say that we get plates set up here and here. I'm going to charge this positive and charge this negative, and then I'm going to introduce some positive charged particles. Okay. Oh, I'm just reading ahead here. Let's see, I'm going to jump back and read some more. It's asking about what will the electric field be if we use 7,000 volts to charge the plates. And we set the plates so that they're only 5 millimeters. Now I know that looks like a big distance between the plates, but the diagrams often are drawn in a manner that allows us to understand what we're doing. And so I drew those, I drew those so that I could label this as there's 7,000 volts. We're going to connect this to a 7,000 volt source. And we're going to set the plates 5 millimeters away from each other. Now it asks initially about what would the electric field be that we're going to end up with. And our assumption has been in the course so far is that if we set up these plates and put a certain potential difference between them, we're treating it as if the electric field in the region between the plates is uniform. Now, we know from talking about in class, and actually, that when you get out to these regions on the edges of this region, the electric field is not going to necessarily be uniform, but in the central region, we often are going to have a pretty good approximation of a uniform electric field. So that's the assumption that we've been making, and we're going to stick with that. So we've shown that for a uniform electric field, we can calculate the electric field, or we can relate the electric field to the electric potential and the separation as just V over D. Okay, so that's a pretty simple relational formula that works if we have a uniform electric field. So I can take the 7,000 volts, divide through by the 5 millimeters, there's the 10 to the minus 3, and the electric field in this region between the plates calculates out to be 1.4 million newtons per coulomb. So pretty good sized electric field that we have. In part B, it says, what would be the kinetic energy and the velocity of an electron that was placed in this region? So let's go ahead and imagine that the charge is being introduced into this electric field region. What if they're electrons? Well, the first thing we got to do is we got to change our diagram. So this had a positive charge on it. We have to flip the plates around. Let's make this one negative and this one positive. This is now negative, and it heads off in that direction. Now, I didn't know that in the first part of the problem, and I didn't bother going back and redrawing this for the negative case, but be aware, you could be asked to draw the two different configurations and show what's going on. So in this problem, we're not looking at acceleration directly. We're not looking at forces. Instead, we're going to do it all in terms of energy is what it looks like. So this becomes an energy problem, and to calculate the potential energy between the two plates for a charged particle, I can take the charge of that particle and multiply by the voltage. So I can go directly to potential energy and say the charge on the electron, that's at 10 to the minus 19. Is that what it looks like? It is, that's at 10 to the minus 19. Times the 7,000 volts, that's 1.12, 10 to the minus 15 joules. Now, that's the potential energy difference for an electron going from one side to the other. That's going to show up as kinetic energy. So once we've determined what the potential energy differences are between locations near the plates, what we can do is say, hey, the electron will acquire this much kinetic energy. So it's going to acquire 1.12, 10 to the minus 15 joules. And then I can go back and say, well, kinetic energy given by 1/2 mv squared, I can solve that for v. So here's the kinetic energy of that electron as it exits the region. So if you remember, we put a mesh here. One of the plates is not solid. There's a mesh, and that means that the electrons, when they come through, they don't get stopped. They can pass through the openings, and they're going to come out with this much kinetic energy. And that says that they're going to be going this fast. So I plugged all the numbers in, I maintained standard units, I put in the mass of an electron. That should have been given, maybe. I mean, we've worked with electrons and protons a lot. You could have those masses written down, but I would certainly provide that if questions came up during the midterm. And so this is how fast. Now that's pretty fast. That's 5 times 10 to the 7th meters per second. That's about 17% of the speed of light. And you guys may be familiar. We'll see this later in this course. So we'll certainly be dealing with the speed of light and what does it mean. And so the speed of light is kind of this ultimate speed, the fastest speed that has meaning, given the way that space and time are constructed. So the way that space and time are interconnected, c is the fastest speed anything can travel. Light, particles of light, photons, are always traveling at that speed. And the formulas that we've developed so far in the course, I know this is always a sad thing to say, they're only accurate, they're only reliable at speeds when you don't get too close to the speed of light. Once you start approaching the speed of light, you're going to need, the formulas we've learned are not adequate. We have to learn a little bit of special relativity, and we'll be doing that in chapter 36, something like that, so not too many weeks away. We'll be looking at special relativity and find out more general formulas for determining kinetic energies. But for right now, 17% of C, that's not too terribly bad. And we would like to use relativity, but we haven't learned it yet. And so we're going to go ahead and stick with this formula for now. This is going to be probably accurate within 1% or 2. So that's how fast the electron is traveling. Now in part C, we're doing the same thing again. Kinetic energy and velocity. This time it's for a proton. So if we did a proton instead, then we'd have to flip the charges on the plates back. So this picture was drawn for the proton. So this now is positive, this is negative, if we want the proton to pick up speed to the right. The kinetic energy is going to be the same. And the kinetic energy is the same because the voltage differences is the same between the two plates. And the charge on the proton matches the charge on the electron. They have opposite signs, but that only shows up in terms of the directions of acceleration. And so the amount of kinetic energy that the proton acquires matches. So these two numbers are the same. And then when we do the velocity calculation, if we give an electron and a proton the same amounts of kinetic energy, the electron's going to be going much, much, much faster. The proton has, 1,800 times as much mass. So the proton is much, much, much more mass. And as a result, it's only traveling at 1.16 million meters per second instead of 50 million meters per second. and it's traveling at less than 1% of the speed of light. Okay, so the speed of light is just kind of a check to tell us how reliable are the numbers we've come up with. And again, looking ahead, when we do special relativity here in 5-6 weeks from now, we'll just learn new formulas that we can use that are more general for carrying out these calculations. Okay, that was problem 1 on the midterm. Did not involve, I'm going to say it did not involve electric forces or electric fields directly. It was just looking at electric potentials and electric potential energies. Now conceptually you want to understand the forces, thinking about how forces are working is useful, but this one was really focused more on chapter 23. It does, let's look at problem 2 though. Let's come back. So any questions on this, let me know, and we'll get those looked at. Now in problem, this is sounding a little bit like that last midterm, so these are maybe good problems, so make sure you do get a look at these problems. These are definitely good problems to take a look at. This time we have 4 objects, and they form a square. And so the picture is going to look something like this. And so what I've got is, I have a square with a charge at each one of the corners. So I should have drawn this picture first. Oh, I did, I guess. I've got the charges. So here are the charges, 1, 2, 3, 4, 3, 4, 1, 2, 3, 4, and they form a square. Now, same as last time, the electric fields are going to cancel out to be 0. That's what the first part of the problem asks about. So this, well, it's not asking about force. So there's nothing where we use the force formula directly. Conceptually, you want to have an understanding of what that is going on, but this is asking about electric fields, and the electric fields in this case are all going to cancel out at that center location because electric fields are vectors. They're related to forces, and each of the charges are the same. Each of the the same mass. The mass doesn't even come into this. The mass was given. Okay, that's fair. But I don't think we're going to use it in this problem. It doesn't sound like. The distance is 10 centimeters again, so all the electric field magnitudes are the same. They're going to cancel out. Okay. And what that's telling us is, again, when we're calculating an electric field, it's kind of anticipating what would happen if another charge came by. If another charge came by, and that charge ends up right at the center, how much force would there be on a charge placed right at the center? So this is all about that particular location in space, and hey, if there was a charge right at that spot, right at the center, it would be experiencing forces from each of the 4 charges surrounding it. But because those charges are the same magnitude and the distances are all the same, the forces would cancel out. So it would be pulled in these 4 different directions. The net effect would be 0 force. And so the electric field also works out for that location to be 0. Doesn't matter how much charge the object has that was placed here, it's not going to feel a force. And that's what E field equal to 0 is telling us. Now, part B in the problem is going in and asking about the electric potential. So we did this with the triangle. Let's do it with the square. And so these distances are the same, r. This time, to get a value of r, let's see, that's a right triangle. That's a 90-degree angle right there. And so r squared plus r squared will equal L squared. Here's the L. R squared, L squared. So I used Pythagorean's theorem and solved for r. And r worked out to be 0.0707 meters. All right? And that seems about right. So the sides are 10 centimeters. We know that these r's are going to be less than 10, but they're also not going to be, they have to be at least as large as 5, and they're coming in at 7.1. That seems about right. So the potentials at the center, the electric potential, V1 plus V2 plus V, is going to be a contribution from all of the surrounding charges. The presence of each of the four charges is going to contribute to the electric potential at the center. So I'm going to have each charge individually provides a potential of kQ over R, and I've got four of those charges. They're each going to contribute. Putting all those numbers, it's another big number. I mean, it's like 1.88 billion volts that we ended up with here. How did that happen? Well, that's a lot of charge. Remember, we said that coulombs are enormous charges, and that's kind of reflected in the electric force constant. The 8.99, 10 to the 9th, the reason that 10 to the 9th is such a big number is because we're using coulombs as the unit of charge. So because we've chosen to use this large charge unit of coulombs, little k, the electric force constant, is really big. Okay, so putting the numbers in, we ended up with that value, and then finally, how much potential? Here we go again. How much potential energy do we have in constructing this? Now let's go back to part B and say one more item here, and that is when we calculate this electric potential, this 1.88 billion volts, what that's saying is if another charge were to come by and end up placed right there, it would require an enormous amount, probably, depending on the charge, I guess, coming in, it could require an enormous amount of energy to be placed at that location. So the electric field is just asking, once the charge is here, how much force would it have acting on it? But the electric potential is about the journey. If a charge comes by, how much energy or how much would be required to bring the charge all the way into that location and place it there? And so it's about the journey, because all during the journey of that charge coming in and finding its way to that center, it's going to be repelled. And so the electric potential and the electric potential energy would be keeping track of all of that energy that needs to be put into that charge to overcome the repulsive effect of the charges that are already there. Again, if this was a negative charge, it would be pulled in and the potential energies would be negative. All right, let's look at this last part of the problem. Here, now again, in part C here, this is keeping track not of another charge coming in, but of the system of four charges that we've already placed. How much energy was required in constructing this system of four charges? So the assumption is, kind of the starting point for all this, is always thinking these four charges used to be far, far away from each other, so far that we could neglect their interactions. But what happened is, maybe one by one, we started bringing these charges in, and what happens is, every time you bring a charge in, well, if charge 1's already here, and I bring in charge 2, that's going to give me a potential energy of U12. And then if I bring charge 3 in, well, that's going to be a potential energy due to the interaction with charge 2 and charge 1. When I bring in that last charge, it's going to be interacting with 1, 2, and 3. Now, we don't have to know the order in which this system of charges was constructed. What we can do is we can look at the final arrangement and say charge 1 and charge 2 are interacting with each other, 2 and 3 are interacting, 3 and 4, 1 and 4, and then 1 and 3 and 2 and 4 are also interacting. So I wrote these 4 in. I guess I should have written the other 2. So there's 4 of them around the edges, 4 interactions we have to calculate. But there's 2 diagonal interactions. And by diagonal, I'm just trying to make sure we keep track of all the interactions. The ones around the edges, there's 4 of those, and in those cases, the potential energy would be kq squared, because there's 2 charges and all the charges are the same, so kind of like q1, q2, divided by distance. And the distance for those would be 0.10 meters. Remember, we want to get everything converted over into standard units, so that when we put in little k, right here, when we put in little k, the units will cancel properly. So little k has meters inside and newtons and coulombs. So 4 of those perimeter interactions and 2 of the diagonal interactions through the center. Now that's going to be given by 2 times r. So that's why we needed to go in and determine what r is equal to. So that's it. I can add together all of the pairwise interactions. Ooh, and it ended up with a scary amount of potential energy. 6 million joules. 6.66, 10 to the 6th joules. That's a lot of 6s. So 6.66 million joules of energy would be required to construct this arrangement of the 4 charges, is the way to think about it. Okay? Questions? Let's look at that next question then. So we looked at the, the first couple problems involve chapters 21, 22, 23. Let's look at, chapter 24 and then 25 and 26 are kind of these last 2 problems. What we've got here is we've got a battery, we've got an arrangement of capacitors. Now, not all the capacitors charge at the same time here. So we have to think there's a sequence of steps. First thing that we're going to do is we're going to close the switch over here, and that's going to charge capacitor 1. So we're going to get capacitor 1 charged first. And then we're going to move the switch over to the other side. Now, when I close it to the left, capacitor 1 charges because of the presence of the battery in the circuit. But when I move the switch to the right, the battery's not in the circuit anymore. The battery is not going to be able to pump charge because there's not a continuous closed path involving the battery. So when we move the switch to the right, we remove the battery from the circuit. And now what's going to happen is we're going to have charge that was on capacitor 1. Some of that charge will migrate over to capacitors 2 and 3. So let's draw some pictures and see how that might happen. So on problem 3 here. So here's the first part. Here's the battery charging capacitor 1. And what we can do is we can just use the formula and say that C1 times V naught, that's 5 nanofarads. I hope we got everything right here. Yeah, 5 nanofarads times 20 volts. We're going to start off when we move the switch to the left with 100 nanocoulombs on the capacitor. So we're going to move that over and let that fully charge to its 100 nanocoulombs. And then we're going to move the switch back the other way. Now when the switch closes over capacitors 2 and 3, what I've done here is I've combined those 2 capacitors. Those are going to be in series with each other. They start out not charged, and now we're going to charge them together in series. And so what I can do is I can use the formula for 2 capacitors in series. Now this is the same formula that we looked at earlier, just written a little differently. You can write C23 as C2 times C3 over C2 plus C3. Now that works if you have 2. If you have 3 or more capacitors in series, that gets more complicated. But that's a handy formula. For myself, I make fewer errors using this. So there's just 2 capacitors being combined in series. I put the capacitances in. I'm getting 3.94 nanofarads. Now capacitor 1 was 5 nanofarads. So the effective capacitance, or the equivalent capacitance, of 2 and 3 is less than capacitor 1. And that kind of suggests that a lot of charge will move to capacitors 2 and 3, but probably less than half, right? Because C1 is, so let's see what happens at equilibrium. What are the conditions at equilibrium that determine how the charges will divide themselves up? How much are going to go over to capacitor 2, 3? How much is going to stay with capacitor 1? And the equilibrium condition is that the two voltages match. So what happens is initially there's a voltage driving charge from capacitor 1 to capacitor 2, but then capacitor 2 begins to acquire a voltage also. And when this side charges, the voltage here goes up. When the two voltages match, then the transfer process stops. So this is going to be the condition we have at equilibrium, that the voltages on the two sides match. And remember, we combined those two capacitors into one as a simplification step. And so what we can do then is say that the voltage on the left side, voltage on the right side match. On the left side, capacitor 1, that's the same thing as Q1 over C1. V23 would be the same thing as Q23 over C23. That gives us a way to calculate Q23 in terms of Q1. Now we don't know Q1 yet, but this does give us a way to substitute and say that, so this is the equilibrium condition where the voltages match. That gives us one equation. And then charge conservation says that whatever the initial charge was, that initial 100 nanocoulombs, that's got to show up at the end of the problem. So the 100 nanocoulombs is stuck. The capacitor can't just discharge because of the presence of the other capacitor. So if this was 100 nanocoulombs in this picture, then these two plates combined, the C1 and the C23, these combined are now going to be the 100 nanocoulombs. And we're trying to find out, of the 100 nanocoulombs, how much went here, how much stayed. And so Q1 plus Q23 needs to add up to Q0. That's condition number 2. So I've got two conditions, I've got two formulas, and what we can do is we can substitute in for Q23 here, and then solve this expression algebraically for Q1. So it's two equations with two unknowns. And it says that the fraction of the charge that stays with capacitor 1 is given by C1 over C1 plus C23. So it says that 56% of the charge stays with capacitor 1. And then when we go back and run the algebra again, the remaining portion is going to go to capacitor 2,3. Now, once we've figured out capacitor 2,3, then we can say, oh yeah, capacitors 2 and 3 were added in series, and that means that capacitor 2,3 is the same thing as capacitor 2, the charge 2,3 is the same thing as charge 2, which is the same thing as charge 3. 2 and 3 charged in series, and then we combine them. Now we can separate them back out and say charge 2 and charge 3 will be equal to 44.1 coulombs. Now I can look at these capacitors and I can actually, I guess I should have drawn these other. So if I look at that picture on part B, here's capacitor 1. This now has 56 coulombs. So here's 56 coulombs of positive charge. Here is 44 coulombs of positive charge, so the 56 and 44 add up to 100. Here's 56 coulombs of negative charge, and here's 44 coulombs of negative charge. So these two plates, this lower one here and the lower one on C3, those add up to the negative 100. What about those two plates? Because those two plates didn't have any charge on them at all to start with. Well, the presence of 56, are these coulombs or these nanocoulombs? These are nanos, okay? Oh, this is a rough one. Okay. These are all nanocoulombs. These are not coulombs. Coulombs are enormous. Okay, that's got to get fixed too. So I'll get that changed into nanocoulombs. Thank you for catching that. Okay, so those are nanocoulombs. So anyway, getting back to this, there was no charge on these plates. Well, now this one is going to have negative 56 nanocoulombs, and this one is going to have, I'm sorry, 44. This is going to be negative 44 nanocoulombs, and this is going to be positive 44 nanocoulombs. So here I've got 56, positive 56 nanocoulombs, negative 56 nanocoulombs. Here I'll have positive 44, negative 44, positive 44, negative 44. So there's still no net charge in that region, but it will, the plates themselves will have charges. All right. So I've got a list of corrections here. That's got to get changed to nanocoulombs. Oh, well, it's only a factor of a billion, right? All right. Billion times too much charge. Let's look at that last big problem from the example. All right, so this is looking at electric voltage. Potential is electric voltage, right? So don't get you know, thrown off by that. Electric potential and electric voltage is the same thing. So the battery has a voltage of 60 volts, or it provides an electric potential of 60 volts. Each of these resistors is directly connected to the terminals of the battery. So each of those resistors is attached to 60 volts. There's 60 volts of electric potential across each one. Those resistors are all in parallel. So that's probably going to make this an easy problem, relatively easy. So, and again, don't count on the midterm problem being as, I mean, if it works out that way, it's fine. But for this particular circuit, each one of the resistors, well, first of all, I'm going to write down their resistances, 10, 20, 30. Here, I did not have to do any kind of a detailed chart. I could just look. Just by inspection of the diagram, I can see that each resistor is getting the full 60 volts. In general, that's not going to be the case. So go back and look at some other examples from homework and from class, from lecture. The voltage in the battery is 60. Each of the resistors is acquiring, has 60 volts across it. So I can go in and calculate the currents by taking the voltage and dividing by the resistor for each individual resistor. So this is kind of a reality check problem. So V over R for resistor 1 gives us 6 amps, then 3 amps, then 2 amps, 6, 3, and 2, 9. That gives us a total of 11 amps. Now, why is that? It says, calculate the current in each one of the resistors, which is what we did, and then how much current is in the battery. So if we think in terms of current flow, what's happening is at this junction, we're getting a flow of 6 amps. So 6 amps is flowing through here, 3 amps here, and 2 amps here. And that means that when I look at this wire over here, the part connected with the battery, that's got to be providing the 3 and the 6 and the 2. That's got to be at 11 amps. So there's 11 amps of current flow here. And then this is 6 of that. So how much current would there be here? Here and here. 6 has gone this way. This would be 5. And this would be 5 here. And then here the 5 splits. 3 goes through here. And 2 goes through here. So, yeah, you should be able to identify the current in each section of that circuit. So any questions on that, let me know. And then calculate the potential drop. So how much voltage is there across each of the resistors? And That's just from the diagram, right? By inspection of the diagram, they're each getting 60 volts. Part C says calculate the rate of electric energy being converted to thermal energy. Now, it's energy would be in joules, but an energy rate would be a power, and that would be in joules per second, which would be watts. So how many watts is each resistor? So resistor 1 is generating thermal energy at 360 joules per second. And I've got that by taking V1 times I1. I can do that for each of the 3 resistors. So for each of the 3 resistors, I can take the electric potential specific to that resistor, multiply it by the current specific to that resistor to get the energy or the power specific to that resistor. So that's an energy rate, which is a power, and that would be 360 joules per second. Resistor 2 is generating thermal energy at 180 joules per second. Resistor 3 would be 120 joules per second. And then D says, what's the power of the battery? Now, there's a couple different approaches here, right? We could say, well, energy conservation says that the rate of energy being used in the resistors, the rate at which electrical energy is being converted to thermal energy, would have to match the power of the battery. Or we could go back and use VI. If you remember, VI works for everything. So no matter whether it's a resistor, a capacitor, a battery, if I get the voltage specific to that device and the current going, for that device, I can calculate the power that way. So the battery is providing, and so C and D are both asking about power. And this is 660 watts. Now, when we talk about, how powerful is that battery, power is not an inherent property of a battery. A battery is determined, a battery's properties are really its voltage. And the voltage is determined by the chemical reactions that are being run within the battery. So once I've identified the chemical reactions within the battery, that's going to determine its voltage. The power of the battery depends on what I hook it up to. So in this case, I've hooked it up to this set of resistors, and in this case, the battery has a power of 660 watts. If it were hooked up to a different set of resistors, there would be a different current, and it would be a different value of power. So, going through these electric circuit problems, it's always good to ask, what are the actual fixed values? So for example, if I build a capacitor, how much capacitance does it have? If I build a resistor, how much resistance does it have? If we construct a battery, what's its voltage going to be? So those are the intrinsic or the inherent properties of those devices. Okay, we're through this. If you guys have questions, definitely stop by. We will get those looked at. And again, make sure that you're looking, these are all good sets of problems. So I would say that all the problems we've looked at today look really good. Problems to go through and understand thoroughly, and then branch out and go back and start reviewing homework or catching up with homework and with examples from lecture. Okay, hope to see many of you in office hours. And we'll stop there for the day.